You think you know what wet means. You've been wet thousands of times. You step out of the shower, your skin is wet. You spill water on your shirt, it's wet. Rain hits your face, you feel wetness. Simple, right? Except you've never actually thought about what that sensation is. What is wetness? Not the word. The actual physical thing happening when you say something feels wet. If this way of thinking helps you see physics more clearly, stay with the channel. Let's start with what you think is happening. You touch water. Water gets on your skin. Your skin feels different. You call that difference wet. But what changed? Your skin is still your skin. The atoms in your hand didn't transform. The nerves are the same nerves. So what exactly is your body detecting when it detects wetness? Think about it. Really think about it. Your brain is receiving some signal and interpreting it as this is wet. What signal? Here's the problem. Wetness isn't a property of water. Water doesn't carry wetness around with it. There's no wetness particle. There's no wet field emanating from liquids. Wetness is something your nervous system constructs from other sensations. It's an interpretation. Your brain takes in certain signals, temperature change, pressure change, maybe something about how your skin is moving, and it concludes wet. But what are those signals actually measuring? Let's go deeper. Put your hand in water. What physically happens at the boundary between your skin and the water? Your skin is made of cells. Cells have membranes. Those membranes are made of molecules, long chain molecules with one end that likes to be near water and one end that doesn't. We call parts of molecules hydrophilic if they're attracted to water, hydrophobic if they're repelled. Your skin cells are covered in these molecules, carefully arranged so the water-hating ends point outward, forming a barrier. Now water molecules arrive. Each water molecule is just two hydrogens stuck to an oxygen. But here's the key thing about water molecules. They're electrical, not charged overall, but the electrons are distributed unevenly. The oxygen hogs the electrons, so it's slightly negative. The hydrogens are left slightly positive. Every water molecule is a tiny electric dipole, plus on one side, minus on the other. And what do these dipoles do? They grab onto each other. The positive end of one water molecule attracts the negative end of another. Hydrogen bonding, we call it. These bonds are constantly forming and breaking. At room temperature, each water molecule is jiggling around, shaking, vibrating, slamming into its neighbors. It grabs onto a neighbor for a fraction of a second, then lets go, then grabs another one. It's a perpetual dance. Billions of molecules forming temporary partnerships, breaking apart, finding new partners. That's what liquid water is. A crowd of molecules loosely holding hands while thrashing around. Not a fixed structure like ice. Not independent like steam. Something in between. Now your skin enters this molecular storm. The water molecules near your skin start interacting with the molecules in your skin. Some of the molecules in your skin are hydrophilic. They want to be near water. The water molecules crowd around them, forming hydrogen bonds. Other parts of your skin molecules are hydrophobic. They try to twist away from the water, but they can't escape because they're attached to the rest of the molecule. So you get this complex interface, water molecules grabbing onto certain parts of your skin, molecules repelling from other parts, all while continuing their frantic jiggling. Here's what your body actually detects. First, temperature. Water conducts heat much better than air. When you put your hand in water, heat flows out of your hand much faster than in air. Your temperature sensors, nerve endings scattered through your skin, suddenly detect rapid cooling. That's signal number one. Cold, or at least colder than before. But you don't just feel cold when you're wet. You feel something else. What? Second signal. Mechanical pressure, but distributed in a strange way. In air, the only pressure on your skin is atmospheric pressure, pushing equally in all directions, so you don't notice it. In water, you get pressure from the water molecules pressing against your skin from the outside, but also molecular forces pulling on your skin from water molecules attaching to hydrophilic sites. It's not uniform pressure. It's spotty, irregular pressure at the molecular level. Your skin has mechanoreceptors that detect these pressure changes. They're reporting something unusual. Not quite like solid contact, not quite like air, something between. Third signal, evaporation. Here's where it gets interesting. When you pull your hand out of water, some water stays on your skin, a thin film of water molecules clinging to the hydrophilic parts of your skin. That film starts evaporating. To evaporate, a water molecule has to break free from its neighbors and fly off into the air. Breaking those hydrogen bonds takes energy. Where does that energy come from? From heat, from your skin. So evaporation cools your skin even more. The faster the evaporation, the more cooling. Your temperature sensors detect this continued cooling even after you're out of the water. Now here's the thing that should bother you. Everything I just described, temperature change, pressure patterns, evaporative cooling, none of that is wetness. Those are physical processes. Your brain receives signals about those processes and creates the sensation you call wetness. But the sensation is constructed. It's an interpretation your nervous system makes because that interpretation was useful to your ancestors. Knowing that you're in contact with liquid helped them survive. So your brain evolved a specific quality, a specific subjective experience, and labeled it wet. But water doesn't feel wet to a fish. Think about that. A fish lives in water. Its entire existence is in water. Does it feel wet? No. Wet is a contrast sensation. It requires knowing what dry feels like. A fish has never been dry, so it has no concept of wet. The fish's skin is always in contact with water. Its temperature sensors aren't detecting a sudden change. Its mechanoreceptors aren't detecting an unusual pressure pattern because water pressure is normal. To a fish, water is just the default state of existence, like air is to you. You don't feel the air on your skin right now, do you? You're surrounded by air molecules slamming into your skin millions of times per second, but you don't feel it. Why not? Because it's constant. Your nervous system filters out constant signals. It's looking for changes. When the air suddenly moves, you feel wind. When humidity increases, you might feel a bit sticky. But normal air? Nothing. Same for the fish in water. Water is nothing special. It's the default. So wetness is relative. It's a comparison your brain makes between the current state and the expected state. When you're dry and you touch water, your brain notices the deviation and creates the wet sensation. But here's where it gets even stranger. You can feel wet without water. If you put your hand in certain oils, they feel wet. Some oils feel almost identical to water in terms of wetness. Why? Because they're producing similar signals. They're cooling your skin through heat conduction. They're creating similar pressure patterns. They might even evaporate and cool your skin further. Or consider this experiment. Put your hand in a sealed bag so no liquid can touch your skin. Now put the sealed bag in water. Your hand will feel something. It won't feel exactly wet, but it will feel cool because heat is conducting through the bag. It will feel pressure from the water pushing on the bag. Your brain might be confused. Is this wet? It's getting some of the signals, but not others. The sensation becomes ambiguous. This reveals that wetness isn't a single thing. It's a bundle of signals that your brain usually receives together and interprets as one unified sensation. Now let's think about what water is doing at the molecular level when it's in contact with your skin. I said water molecules are jiggling, vibrating, slamming into each other. How fast? At room temperature, a water molecule is moving at about 500 meters per second. That's faster than sound. These molecules are screaming around, colliding billions of times per second. Every collision involves electromagnetic forces. The electrons in one molecule repel the electrons in another molecule. The positive nuclei attract the electrons. It's a continuous storm of electromagnetic interactions happening faster than you can imagine. When a water molecule hits your skin, it's transferring momentum. Millions of molecules hitting your skin every second, each one transferring a tiny amount of momentum. That's pressure. That's what pressure is, not some abstract force. It's literally molecules slamming into a surface. But because there are so many molecules and the collisions are so random, the pressure averages out to feel smooth and continuous. You don't feel individual molecular impact. You feel the statistical average of countless impacts. And temperature? Temperature is just the average kinetic energy of those molecules. Hotter water means the molecules are moving faster, hitting harder, more energetically. Colder water means slower molecules, gentler impacts. When you put your hand in hot water, you're being bombarded by faster moving molecules. They're transferring more energy to the molecules in your skin. Your skin molecules start jiggling faster. That increase in molecular jiggling is what your temperature sensors detect. They're not measuring some abstract quantity called temperature. They're measuring how much their own molecules are being shaken. Here's something that should completely change how you think about touch. I said the water molecules are hitting your skin. But remember what I told you about touch. You never actually touch anything. The electrons in the water molecules repel the electrons in your skin molecules. There's always a tiny gap. The water molecules get close to your skin molecules, the electromagnetic forces get stronger, the molecules bounce off. So when you feel wet, you're feeling electromagnetic repulsion from billions of molecules bouncing off your skin at high speed. Wetness is an electromagnetic phenomenon. But there's another layer. Water molecules aren't just bouncing off. Some are forming hydrogen bonds with molecules in your skin. A hydrogen bond is a partial sharing of an electron between a hydrogen in one molecule and an oxygen or nitrogen in another molecule. It's weaker than a full chemical bond, but it's real. These bonds are constantly forming and breaking. Each bond lasts only a tiny fraction of a second, then breaks, then reforms with a different partner. So at any moment, your skin is loosely bonded to the water through millions of temporary hydrogen bonds. Think about what that means. The water isn't just sitting on your skin. It's interacting with your skin at the molecular level. Parts of your skin molecules are grabbing onto water molecules. The water is grabbing back. This mutual grabbing is what makes water stick to your skin. This is why when you pull your hand out of water, some water comes with you. The hydrogen bonds between water and your skin are strong enough to pull water molecules away from the bulk liquid. Those molecules then stick to your skin until evaporation takes them away or you wipe them off. And evaporation, that's a fascinating process. Why does water evaporate? A water molecule in the bulk liquid is surrounded by other water molecules, all hydrogen bonding to each other. To escape, a molecule has to break those bonds. That requires energy. Most molecules don't have enough energy. They're stuck. But there's a distribution of energies. Some molecules, by random chance, have more kinetic energy than average. If one of those high-energy molecules is near the surface and happens to be moving upward, it might have enough energy to break free. It shoots out into the air, that's evaporation. The molecule that escapes was above average in energy. When it leaves, it takes that excess energy with it. So the average energy of the remaining water decreases. The water gets cooler. This is why evaporation cools things down. It's not just that the phase change requires energy, though that's part of it. It's that the molecules that escape are the hot ones, the fast ones. They leave, and the slow ones remain. The average speed decreases. Temperature drops. Your skin is covered with water after you step out of the shower. Molecules are constantly escaping from that water layer. Each one takes energy from your skin. Your skin gets cooler. You feel cold. That's why wet skin feels colder than dry skin, even at the same air temperature. It's not the water that's cold. It's the evaporation. You're being cooled by the departure of high-energy water molecules. If you stand in front of a fan, the effect is much stronger. Why? Because the fan blows away the water vapor near your skin. More water can evaporate into the air. More molecules escape. More energy is removed. You feel colder. Now let's ask a harder question. Why does water stick to some things and not others? Why does water bead up on a freshly waxed car but spread out on glass? This is about those hydrophobic and hydrophilic molecules. Glass has lots of oxygen atoms on its surface. Oxygen is electronegative. It attracts the hydrogen in water molecules. Hydrogen bonds form easily. Water molecules crowd around the glass surface, forming a thin film. The water spreads out. We say glass is hydrophilic. Wax is made of long hydrocarbon chains, carbon and hydrogen sharing electrons fairly equally. No strong electric dipoles. The electrons are spread out evenly. Water molecules can't grab onto anything. There are no good spots to form hydrogen bonds, so the water molecules prefer to stick to each other rather than to the wax. They pull together into droplets to minimize contact with the wax. We say wax is hydrophobic. But notice, it's not that wax repels water, it's that water prefers itself over wax. The water molecules would rather hydrogen bond to each other than sit next to boring, nonpolar hydrocarbon chains. Your skin is somewhere in between. Parts of your skin are hydrophilic, parts are hydrophobic. That's why water both sticks to your skin and can be wiped off fairly easily. If your skin were entirely hydrophilic like glass, water would form a thin film you couldn't remove. If it were entirely hydrophobic like wax, water would bead up and roll off immediately. But evolution found a balance. Your skin needs to interact with water for various biological reasons. Sweat evaporating to cool you down, moisture maintaining flexibility. But you also need to be able to shed water so you don't stay wet forever. The mix of hydrophilic and hydrophobic molecules gives you both. Here's something most people never think about. The sensation of wetness changes depending on context. Cold water feels more wet than warm water. Why? Because cold water conducts heat faster and evaporates slower. Your temperature sensors are screaming that something's wrong, and your brain interprets that as increased wetness. Similarly, water feels more wet when you weren't expecting it. Surprise wetness feels wetter than intentional wetness. That's your brain amplifying unexpected signals. If you're paying attention to every detail, ready to feel water, it feels less wet than if water suddenly splashes on you out of nowhere. There's also a time component. The first moment of wetness feels different than being wet for a while. Your mechanoreceptors adapt. After a few seconds, they stop reporting the unusual pressure patterns because those patterns are now the new normal. Your temperature sensors adapt too, though more slowly. After a minute in water, you don't feel as cold as you did at first, even though your skin temperature might still be dropping. Your nervous system adjusts its baseline. This is why when you jump in a cold pool, it feels shockingly cold at first, but after a minute, it feels almost normal. Your brain has recalibrated what normal means. Let me tell you something that will completely change how you experience wetness. Everything I've described, all these molecular interactions, electromagnetic forces, thermal conduction, evaporation, pressure sensing, all of it is happening continuously right now. The air around you has water vapor in it. Those water molecules are colliding with your skin. Some are sticking temporarily, forming hydrogen bonds, then evaporating away. Your skin is constantly interacting with water at the molecular level, but you don't feel wet because the amount of water is small and the rate of evaporation equals the rate of arrival. There's an equilibrium. When humidity increases, more water molecules arrive than leave. A thin layer builds up. Your skin can't evaporate water fast enough. You start to feel sticky, which is a mild form of wetness. When humidity is low, water evaporates faster. Your skin dries out. You might feel dry, tight, uncomfortable. Wetness isn't binary. It's a spectrum. At one end, completely dry, which is actually uncomfortable. At the other end, soaking wet, also uncomfortable. Somewhere in the middle, There's an optimal moisture level where your skin feels normal. That's the level your body tries to maintain. And here's the deepest thing. The sensation of wetness is one of the most basic sensory experiences you have. You learned what wet means before you could talk. Babies know wet. They don't like it. Wet diaper, cry. Dry diaper, happy. This suggests that the sensation of wetness is primitive, deeply built into your nervous system. It's not something you had to learn to interpret. Your brain comes pre-wired with the concept that certain signal combinations mean wet, and wet is generally bad because historically being wet often meant danger, cold, discomfort, vulnerability. But what does this tell us about reality? It tells us that every sensation you experience is constructed. You think you're directly perceiving the world, but you're not. You're receiving electromagnetic signals from nerve endings. Your brain interprets those signals and creates a sensory experience. Wetness doesn't exist out there in the world. It exists in your brain. Water exists. Molecules exist. Electromagnetic forces exist. But wetness, that's an interpretation. It's a story your brain tells you about what's happening. Does that make wetness less real? No. It makes it different.